Welcome to this video lecture on SQL basics. What I am going to tell you is the following. First, what is SQL? I will define the language concept, and then I will present you relational operators of SQL because SQL is a relational language. And then we are also going to see what set-oriented operators they are in SQL because SQL is a set-oriented language in the sense that tables are sets of tuples or rows. And SQL operates on rows and tables of data. Then we will also see what kind of data definition and manipulation options there are in SQL. And we are going to work with an example database, the uni database. And we are also going to cover other essential functions of SQL. So how do we interact with the database? There are different roles. For example, data analysts query, analyze, and manipulate tables. Data architects define tables and formats. They describe data using metadata. Application programmers query, manipulate, or delete tables. And database specialists, they install, check, and safeguard tables and assign user permissions. And all these operations are usually done using a database language, mostly. There are also graphical tools for this, but still there exists a database language or several database languages that allow this interaction with the database system. And one of these languages, and probably the most widely used one, is SQL. What is SQL? Historically, SQL is a further development of SQL. SQL was a research prototype at IBM Research in the 1970s. It was created for System R, and it was the first executable relational database management system. The paper was published by Chamberlain and Boyce. SQL, a structured English query language. And the idea was that you can interact with the database using structured English. So you have words like select, from, where, count, group by, etc. that are, of course, words from the English language, but there's a clear syntax, a clear structure, how these words are composed together to formulate database queries. And this research prototype was then further developed into a product that was put on the market in 1979 by Relational Software, which is known today as Oracle Corporation. They introduced a new version of SQL in a software that was called Oracle. It was published for VAX computers, and the language was now called SQL, Structured Query Language. But because of these historical roots, some people today still pronounce the abbreviation SQL as SQL. And SQL was then standardized by the International Standards Organization, ISO. And the first standard was in 1996, but there were other standards, 89, 92, 99, and so on. And today, SQL is a really powerful language. We say it's as powerful as relational algebra, and it is considered a relationally complete language. So a relationally complete language is a language that allows to interact with relations in a way that is at least as powerful as the relational algebra. And SQL has been the leading language for database interactions for decades. On the new SQL, many NoSQL systems now also offer an SQL or SQL-like language interface. So now please think about the following question. SQL is over 40 years old, and in computing, 40 years is like prehistoric, right? So the question is really, why is this old prehistoric language still in use so widely? Or again, I mean, in many cases, SQL is becoming more important again. So what could be a reason for this, or what are the possible reasons for this? Please think about this and bring your possible answers to class. So a little bit more detail on relationally complete database languages. SQL is as powerful as relational algebra. That's what I said before. This means in more detail that at least the operators of relational algebra can be represented by it. So you can read this in chapter 3.2 in the book. So you should be able to do selection. So you choose the rows you want to see in your query. You can project rows, you can project columns, which means you can choose the columns you would like to see of the table. There's a Cartesian product which generates a set of all possible combinations of rows from two tables. And plus you need set-based union and difference. And if these operators are supported, then a language is called relationally complete. And in case columns have no order, which is the case in SQL, you also need renaming to eliminate duplicate column names. Okay, so let's see what kind of relational operators there are in SQL. The first one, or the basic structure, is select, from, and where. Three English keywords where you indicate the attributes you like to select, or columns from a table. You indicate the table to be searched, and you also indicate the conditions for rows of the columns. So you have an output, an input, and processing. So interestingly, the select clause is not the selection in the sense of relational algebra. The select clause is actually the projection, the selection of columns. The where statement is actually the selection condition for rows, and the where statement is the selection in the sense of relational algebra. So here's an example. Here's a table of employees, and if we just select sub and name, these two columns, from the table employee, then what you get is this result. So we just select two columns, two attributes from this table. Okay. Now, if we just project this table on one column, then technically you remove duplicates, because relations are defined in a set-oriented way, and a set can only contain unique elements. So if we say that a table is a set of rows, then it means that every row has to be unique, and then we can talk about a relation. However, in SQL, this is not the case by default. So only if you have a primary key, then it is a relation. A table without a primary key, also query results, for example, they are not relations per se, they're tables, and you can have duplicates. If you don't want duplicates, you need to indicate it with the distinct keyword. So if you select distinct city from employee, then you get this result here, where the duplicate Kent here is removed. So this is a projection projection in the sense of relational algebra, and this is noted in algebraic notation using the pi symbol. Now here is the selection. Now, for example, we want to select employees that live in Kent and are subordinated to department D6. Now, if we indicate an asterisk in the select clause, this means that we take all columns into account. Now, this example results in this result set here. It's just one row that fulfills all criteria. So this is a selection in the sense of relational algebra, and it is noted using the sigma symbol. Now we have already two operators that we need for relational completeness. The third is Cartesian product. The Cartesian product creates all possible permutations of two tables. Now here's the example. We have two tables, employee and department. Now the Cartesian product creates all possible permutations, all possible combinations of rows, as you see here. Syntactically, this is the syntax. So you select all these columns and you select them from employee, comma, department. So this comma notation is actually the Cartesian product. However, what you see here in yellow are the combinations that actually make sense. Why? Because the subordination of the department should correspond to the department number. So the Cartesian product usually is combined with a selection. And that we see here. We have the Cartesian product here above. And then we combine it with a selection. So we combine the from clause with the where clause. We indicate now that we want to select the employees whose subordination corresponds to the department number. And what we get then is a so-called join or inner join. So we have the result set here, and we have selected all the employees together with the department name. So this basically answers the question, which employee works in which department. Now we also need renaming because table order matters. So here's an example. Now we select from a table called Sports Club. This is the table. You have an employee number, name, street, city. And we want to create a sports competition where every participant of the sport, where every member of the sports club competes against every other member of the sports club. So how do we do this? We select from the Cartesian product those rows where the employee number of the first instance of the table is different from the employee number of the second instance of the table. And this is the output that we get. However, now we have the problem that the employee number in the two instances has the same name. So how do we disambiguate this in the query? We can use a construct called aliases. So we give sports club the first instance of this table, the alias S1, and we give the second instance of this table that we select in this clause, the alias S2. And then we can disambiguate the employee number and say S1 employee number is not equal to S2 employee number. And we also select S1 name as participant 1 and S2 name as participant 2. So this is renaming using aliases in SQL. Now another question for you to think about this also a little bit further. Now, what is the difference between a relation and a set? I have already talked about this in this video, so you can find the answer. But you should also think further and say, well, what does this have to do with database systems and SQL? So why is it relevant? So here you see the instance of a set. You see an example of a set. And here you see an example of a relation. Think about this and bring the answers to class. We'll discuss it then. So we have covered the relational operators of SQL that makes it relationally complete. Now let's see what kind of set-oriented operators there are. So set union is an important set operator that combines two sets by taking all the elements into account that are elements of either one of those two sets. So here you have an example. We have a sports club with 3 members and a photo club with 2 members, and we can define the table club members as the table that combines the two tables, so club members are either sports club members or photo club members. And then we have 4 elements. Why 4? Because employee E7, Mr. Howard, is member of both clubs. Now in a mathematical notation, we have this union symbol. In SQL, we just write it out as English keyword union. So we select all columns from the sports club table and we unify this with the selection of all columns from the photo club table. This is the result of this SQL operation. Now, there's just one restriction. To be able to unify two tables, they need to be union compatible, which means they need to have the same number of columns together with compatible data types. So this is the case here, so we can unify these two tables. There's also intersection. In SQL, there is in some database systems an except or minus operator, not in MySQL. There you have to do it with the in operator. So we select all columns from sports club and only those rows where the employee numbers is also in the photo club. And here you see we have a subquery using a nested notation using parentheses. So here we have the sports club again, the photo club, and the result of the intersection is only one row, row E7, because Howard is a member of both clubs. We also have set difference, and also this can be expressed in SQL using the not in notation. So we select certain features. Now let's see. What we want to do here is a competition. So here's the mathematical notation. The sports club without the photo club is combined using a Cartesian product with the photo club. So every member of the sports club that is not member of the photo club competes against all members of the photo club. In SQL, this is written in this way. We select from the Cartesian product of sports club and photo club, where the employee number of the sport club member is not in the list of employee numbers from the photo club members. Here's another one to think about. So SQL is a query language. However, probably querying data is not enough. So what other functions does a language need? What other functions does a database-specific language need? Well, one example is data definition and manipulation. But if you look at the SQL standards today, it's much more than a query language. And also it's much more than a query and manipulation language. You can do so much with SQL. But one of the things we need to do in practice is also to define and manipulate data, and we're going to see how this is done with SQL. So the first thing we need to do is, of course, create tables, because if there are no tables, there's no data to be stored. So that probably you have already found out when you installed your first database server. It's empty in the beginning. So what do? We can create tables using this syntax here, the create table notation. So create table and then the name of the table, and then we indicate a comma-separated list of column definitions. And a column definition starts with the name of the column and then the data type and maybe other attributes such as not null, which indicates that it cannot be empty. There are other data types, for example, character or variable character or integer or floating point, date time. So this is indicated in the manual of the database system you're working with, and there are some standardized data types, but there are also database system specific data types. So you'll have to check that. Now there's also the opposite of create table. It's called drop table, and it lets you delete table definitions. And with alter table, you can change table definitions. Now you have a table, you want to insert data into it, and this you can also use for your project. Using the insert command, you can insert data into a table. So for example, here insert into employees, then values, and what follows is a comma-separated list of tuples or rows, which need to correspond to the table definition. It can also be only just one row or a list of 1000 rows. What you have to keep in mind here is that the insert command is not so efficient. So to load lots of data, which is called a bulk load, you will probably want to use a data migration tool, or in the case of MySQL, for example, the load command, which loads comma-separated value files directly into a table. Also, the MySQL workbench, if you use the table import wizard, it translates files into insert commands, and there you have a performance bottleneck. Just to give you a heads up. And then perhaps you also want to delete data. So this is done using the delete command, delete from employee where city equals Basilea. Now the delete command is set oriented, and it deletes all tuples that correspond to the criteria here. If you have no criteria, the whole table is emptied. The same is also for the update command. So if you want to change existing data, you can use the update command. Here's the example. Update employee, set city to Basilea, where city equals Basel. Again, this is a set-oriented command. It will update all rows that correspond to the selection criteria here. So you need to be careful about this definition of update statements. Now let's see a small example, and I invite you to also stop the video and use your MySQL installation to do the exercises with me together. In this way you will learn the most from this lecture. Database server running at the Enterprise Lab. The address is db.enterpriselab.ch, and using your MySQL Workbench you can log into this database server using the user DKS and the password indicated here. So I'm going to show you this. I've prepared this connection already here. Now, if you open MySQL Workbench, what you see is here a list of databases, and in every database you have certain tables. Here's the English version, and for example, you can just look at the table using this icon here. Okay, so that's how you log in into the server. When you start MySQL, you come to the MySQL Workbench home screen, and here you can create a new connection, and here you can indicate the parameters as shown on the slide. Okay, now here you can execute the query. Let's see this as an example. You just write the select statement here and you push this button, and the result of the query is shown in the result window. So what kind of data is there in this database server? So this is the data structure that is in this database server. We have students who attend lectures, example students who attend example lectures, professors that give lectures, and there are also examinations with grades. So if you want, you can also look at the relational schema of the database using the reverse engineer function. So database, reverse engineer. Now here we choose the database connection. Okay. We choose the database to reverse engineer. Now we import all table objects. Continue. Close. Now you see here, this is the extended entity relationship diagram for MySQL Workbench that shows now all the tables together with foreign keys and data types. It's all there. Okay. Here you have the example data. So you see it's a very small database. It fits on one page. Now let's do some finger exercises. So I recommend that you do this now together with me. So try to find the solution first. I'm going to present the solution after that. So what are the names of the students with more than 10 semesters? So I think that's an easy one. So the students with more than 10 semesters. Oh, no, there is a error. What is it? Students doesn't exist. Okay, so you make sure that you double click on this database name so that the database is used. Now it works. You can also write use dbm _n. Okay, that works too. So now you see these are the two example students who have studied for more than 10 semesters. Here's the solution. A second finger exercise. What is the name of the professor who gives the ethics lecture. Oh, the solution is already there. What was it? The name of the professor, name from professors. Where? Oh, no. That's different now because we need the lecture first. Huh? I can highlight part of the code and only execute this. So there's no lecture, of course, because I missed an H. Now let's do this again. Okay. Now you see, it's given by employee number 2125. We can solve this with a join. So that's the Cartesian product, and now we need also a join condition. So given by should be equal to the ID of the professor, first ID, and the title should be ethics. Now if I use proper semicolons, then I can also use this arrow, this flash here, which executes the current statement. Then I don't need to highlight the code I want to execute. Okay, so here we see it's Socrates, the name. Now we just make a projection. Okay, there you go. That's the solution. Here's another finger exercise. What are the names of the students, of all the students of Socrates? Now this seems like an easy one, but actually it's a little bit more different, more difficult. So now let's find first all the lectures given by Socrates. So we just delete the restriction on one lecture. And now we want to find all the students that attend these lectures. However, now we see that there's a relationship table called attend. This relationship table puts into relation a student ID and a lecture ID. So for every student and every lecture combination, there's one row in this table. And then, of course, you also need the student table to get the name of all these students. Because here we just have student IDs and lecture IDs. So what we need are now all these join conditions. So given by is equal to person ID and now we want to compare lecture IDs, but you see it has the same name. So we need to disambiguate this this column. So from the table lectures, lecture ID must be equal to attend lecture ID. Okay, and so we have joined lectures and professors, we have joined lectures and attend, and now we also need to join attend and students. And of course, we also need to restrict the professor name. Okay, let's see what this does. There's an error. Student doesn't exist, so it's actually students with an S. Have it twice. Column name is ambiguous. Select student names. Okay, there you go. That's the solution. Now you could do this differently. You could do this differently. I have just chosen the table names as aliases, but you could also define your own alias here. For example, Professor's P, then P is your alias that you can use. So there are other essential SQL functions. There's string comparison with like. It's like a wildcard. It's a placeholder. For example, a percentage sign can replace any number of characters. An underscore sign can replace exactly one character. Now look at these two examples of SQL statements. What do you think? Which of the lectures from this example database are selected? And what's the difference between the first statement and the second one? There's also different comparison operators. For example, you can use the greater or equal sign or the less than or equal. And it's equivalent to saying the semester is between 1 and 4. So this between and notation is basically equivalent. And you can also use the in operator. So here semester is in 1, 2, 3, 4. Another important function of SQL is sorting. So I can sort data by columns, either ascending or descending. So look at this example here and try to think, what does this query do? The result set is indicated here. Aggregate functions. So an aggregate function calculates a single scalar value from a set of values. For example, counting the number of values, counting the number of distinct values, summation, average, maximum value, minimum value. Now let's look at this SQL syntax. Select count employee number from employee where sub equals D6. What do you think is the result of this query? That's right, 2, the number 2. We have 2 employees with sub equals D6. Now this can also be grouped. So instead of just selecting where sub equals D6, we can group by the variable sub, and then this counting is computed for every value of this column. So in this case, what is the result of this query? Select count, employee number, sub, from employee group by sub. Okay, so now here we have 3 sub values, D6, D3, and D5. And for every category, we get a count. So we have 2, D6, 1, D3, 1, D5. We get 3 columns with these values. There are also subqueries, and here's a motivation why we need to do this. So for example, we want to calculate the average number of lectures per week that the professor has. So it's the average of the total ECTS per professor. You see, in SQL, you cannot nest 2 aggregate functions. So we cannot take the average of a sum directly. This produces an error. However, we can resolve this using subqueries. So here you see that's an example of a subquery. We select from, and here's a parenthesis and an alias, and then this subquery can be used like a table or view. It's called an inline view. And we can formulate another nested query in there. So what's the average number of lectures per week that the professor has? Okay, we open a parenthesis, and then here we calculate the sum of ECTS per person ID and name. We call this sum ECTS. And one level higher, we just select the average of this new column. And this works. Okay, so that was SQL basics. These are 11 learning objectives that I have for you in this video. So simple queries, select from where, simple filter criteria, equal, less or equal, less than, and or not. We have queries across several tables, join, the common notation, and the where function. Then we have set operators. We've covered in, not in, and union. We've seen how to create a table and also how to delete the table, how to change tables using insert, update, and delete commands. We have looked at comparison operators between, in, like. We've seen how to sort tables, order by, ascending, descending. We've seen how to remove duplicates using distinct. We have covered aggregations, count, sum, average, minimum, maximum, group by, and subqueries. So if you have any questions, bring them to class. We'll discuss them there. And now I recommend you do the exercise on SQL basics. Thank you for watching. Thank you for your attention, and we'll see each other in class in the interactive session. Goodbye.